Example 5.3.3. This one says, the equipment in your restaurant's kitchen needs replacement, including the ovens, cooking surfaces, dishwasher, and refrigerator, freezer. You plan to finance the purchase of new equipment through your bank. Looking at your budget, you believe you can afford a loan payment of $850 per month. Your bank is offering financing at 5% APR over 36 months. What is the maximum you can borrow and be within your budget? Okay, we've got another time value money problem, so we're going to use that three-step process again, where we're going to start by drawing a timeline to map out our cash flows. And then we can use that cash flow map to figure out what type of problem we're looking at here, what type of cash flow we're looking at. And then once we know what type of cash flow we're looking at, we can select the appropriate tool to be able to evaluate it. So let's start by mapping this guy out. All right, so we want to know how much we can borrow from the bank today. So what are we going to do today? And we're going to be able to repay a maximum of $850. So I'm going to look at that from the perspective of the borrower. So I'm going to call that a cash outflow of $850 1 month from now, another one 2 months from now, and then that pattern will continue for 36 months. And on the 36th month, we'll have our final payment of $850. The only other piece of information we are missing is what is the interest rate on this loan. And with this one, we've got the extra wrinkle that we didn't have in the previous chapters, and that is that we have the interest rate reported as an APR, or annual percentage rate, but the cash flows are happening monthly. Well, the interest rate we use to evaluate the cash flows, whether we're going to use the calculator, formulas, or Excel, or a spreadsheet, that interest rate needs to be the effective rate that matches the frequency of the cash flows. Since these cash flows are happening monthly, we need to find the monthly effective rate to plug in as our discount rate. Okay? And the way we can get that is by using the definition of APR. If we look on our formula sheet, on the Chapter 5 formulas, we have the definition of APR right here, where APR is equal to little r times m, where r is that periodic effective rate. In this case, the monthly effective rate, because we have monthly cash flows, and then m is the number of compounding periods per year. Well, with this problem, we know the APR, that's 5%. We don't know the monthly effective rate. We want to find that, but we do know there are 12 compounding periods per year. So we can use this definition to figure out that little r, that monthly effective rate. All right, so we just want to solve for r by dividing both sides by 12. And I'll flip r over to the left-hand side since that's just how we're used to looking at it. All right, so our monthly effective rate is roughly 0.4167. And I used 5 here, 5%, so the number I got back is also in percentage format. So our R that goes on the timeline is 0.4167%. Okay, so we've got all of the information mapped on, all the information from the problem mapped onto a timeline. We know the monthly payment, we know how many payments, we know the interest rate, the effective interest rate that matches the frequency of the payments. So, and we actually already know that we're going to be solving for present value of something, some type of cash flow, because we just need to know how much we're going to borrow today, and then we're going to make these payments to repay the loan over time. The next question to answer is, what type of cash flow are we looking at here? Well, we've got level payments. It's $850 per month over 36 months. They stop at some point. So, there are 3 choices: are lump sum, annuity, or perpetuity. Well, we know we can throw perpetuity out because those last forever. It's definitely not that. A lump sum will always work, but if we can figure out that this is one of our three types of annuities, then we can use shortcuts to solve it, either the time value money keys in the calculator or one of the annuity formulas that will save us from having to treat each cash flow individually like we would have to do with the lump sum formula. So let's take a look at our cheat sheet and see if we can find a pattern that matches this one. We've got the first payment at the end of month 1, second payment at the end of month 2, and the final payment at the end of month 36. Right, if we scroll down to annuities on our cheat sheet, it starts with an ordinary annuity. And an ordinary annuity is a finite series of equal cash flows at regular intervals paid at the end of each period. And if we look at the timeline for an ordinary annuity, we've got one that looks like it matches what we're dealing with here. We've got the first cash flow at the end of the first period, second one at the end of the second period, and the last one at the end of the last period. So looks like that's what we're dealing with. We'll just compare to the annuity due and growing annuity to be sure. If we look at the annuity due, the only difference here is that the cash flows happen at the beginning of each period. And if that's what we were dealing with, we'd actually have the first payment at time period 0. It would be today at the beginning of month 1, and the last payment at the beginning of the last period. And we have this blank spot out on the end of the timeline instead of at the beginning. This doesn't look like what we're dealing with. I don't think it's an annuity due. And then growing annuity, those cash flows change at a set rate over time. So we know that's not what we're dealing with. It's because our problem has level cash flows that don't change. Okay, so it looks like we're dealing with an ordinary annuity. So once we've identified this guy, we know what tools are available to deal with this problem. We can use either the present value, future value of an ordinary annuity formula, the time value money keys on a financial calculator, or a spreadsheet. We're going to sidestep the spreadsheet just because that is not usually available to us, although I certainly encourage you to explore the spreadsheet solutions that are in the text if you want to use this stuff outside of an exam. That's typically I'll reach for a spreadsheet when I'm solving these type of problems, unless it's just a real quick one. The formulas, if we were going to use the formulas, we've got two to choose from, either the present value or future value of an ordinary annuity. And either one would work. It just kind of depends on what we're solving for. We'll pick the one that requires the fewest number of steps in order to solve. And in this case, it's pretty straightforward. We're looking for the value of these cash flows as of today at time period 0. So that'd be the present value of an ordinary annuity. And just for the sake of, we won't actually go through solving the problem, but I do want to set up the formula because it'll make a point about why we want to be pretty exact with this interest rate. So the present value of an annuity formula, let's say in this case at time period 0, is equal to the first payment, time period 1, divided by R, and that is all multiplied by 1 over 1 plus the interest rate raised to the R, and then that whole thing is also raised to the N, or the number of compounding periods per year. And that's just a present value of an ordinary annuity formula that we've used over and over again at this point. So let's plug in the numbers. I won't make you sit through solving it. I guess you could skip ahead anyway. I wouldn't be making you do it in any case, but we won't take the time to actually solve this one. I just want to show what's going on with the math here and why we need to be pretty careful with this interest rate. So the payment on this one is $850 per month. The interest rate here for R, since we're doing arithmetic with it, we need to actually use the decimal version instead of the percentage format. So we would actually plug in 0.004167. Right? Just moved the decimal 2 places to the left to convert it from percentage to decimal format. Oops, we know what the N is, don't we? That's 36. Let's see if we can be a little better about that. Okay. Actually get that 1 in there. Now, this is the part that I wanted to look at so we'd know why we want to be really careful when we're using the calculator. The the interest rate that we're plugging in here, and the calculator is just going to solve this formula for us. Notice that that thing is raised to the 36 here. So any rounding error we introduce by using, for example, a 4 decimal approximation is going to get magnified exponentially 36 times. So with these type of problems, these rounding errors start to show up and can actually make it really difficult to select the correct answer from the choices, because it may be far enough off that it's difficult to tell which one is right. So although we're going to jump right to the calculator solution, we do want to be really careful with this interest rate, and we'll talk about how to do that as we go here. Okay, let's look at solving this guy with the time value money keys. I'm going to set up my calculator entries vertically, going in the same order that they appear on the calculator, where n is the total number of payments or total number of compounding periods. Those two things are equivalent with an annuity. In this case, that's 36. We're going to make 36 total payments, right? If we look at our timeline, the last one there is at the end of month 36. Our interest rate per year, I'm actually, instead of writing the 4 decimal approximation, I'm going to write in 5 divided by 12 to remind myself that I actually want to have the calculator do that division before I plug it in. I don't want to type in that 4 decimal approximation. Present value is what we're looking for, so put a question mark there. Payment, looking at this from the perspective of the borrower, that's going to be a cash outflow of $850. And then future value is 0, not because the future value of this annuity is 0, it certainly isn't, but what we plug on these 3 cash flow keys, the present value, the payment, and the future value, are the actual cash flows that happen at the corresponding part of the timeline, where present value is at tick mark 0, future value is a cash flow at the last tick mark, and then payment is what happens over and over again throughout the timeline. With this one, we of course do have an $850 payment at the end of the timeline, so it may be tempting to put that there for future value, but when we put it on the payment key, we put $850 on the payment key and then set n to 36, it has already accounted for this last payment. We'd only put something on the future value if there were an additional payment over and above that last one, which there is not in this case. So future value is going to be 0. All right, let's plug these guys in. I'm going to start by hitting second clear TVM to zero everything out on those keys, and I'm just going to work left to right. N is 36, so type in 36 and press N to store it. I over Y is that 5 divided by 12, and rather than typing in, I know I already typed it in, but rather than typing in as 0.4167, I am instead going to have the calculator do 5 divided by 12 and press equals to have it do that division. And although it's showing me 4 decimal places, it's worked out to about 13 internally. So if while this number is on the display, I press the I over Y key, it actually stores that 13 decimal version of that number. And so I'm going to get a much more precise answer than I would if I just typed in 0.4167. All right, present value is what we're solving for, so we'll skip over that. Payment is $850 as a negative because it's a cash outflow. We'll press payment to store it. And then future value is 0, which it should already be because we cleared out the time value money keys, but just to be sure, we'll go ahead and type it in. All right, now we want to solve for present value. We've got 4 of the 5 variables recorded, so the calculator can solve for the 5th for us, present value in this case, and we do that by hitting compute present value, and we get $28,360 and roughly 85 cents. So we can borrow up to $28,360.85, and that will, if we borrow exactly that and repay it over 36 months, then our monthly payment as we repay that loan will be $850. So if we were to put that on the timeline, that would be a cash inflow right here of $28,360.85, which of course we would turn around and use to buy equipment. But in terms of just the loan, which is what we're looking at here, we would receive the $28,000 today, and then we would repay it over 36 months at $850 a month.